In this playlist, I'm going to go through exam 2 from spring 2018 in my Thermo 1 class. On the left hand of the screen, you see the exam, and the right hand, I show the scope document. Admittedly, this particular scope document, I think, is actually newer than 2018, but hopefully it's not too different from what the students at the time saw. In this playlist, I'll have a separate video for each problem, but what I'd like to do right now is just scroll through the exam and talk about how I would approach it. Remember, with these exams, you tend to be time limited and you want to get as many points as possible. So I usually will read the whole exam. And by the way, the reason we're looking at the scope document is just so that we can recognize how the different topics are actually incorporated into the exam. So problem 1 is a thermocalculus problem. So in this, we're asked ideal gas, prove that DHDP is equal to 0. And then you're given a solid characterized by a volume expansivity and an isothermal compressibility. And then we need to derive a formula that can be used to calculate entropy changes between two different temperatures and volumes. So let's take a look at the scope document. So this will tend to focus on the topics towards the bottom. So fundamental property relations, Maxwell relations, and general calculus concepts. In problem 2, we have a heat exchanger, which would be perhaps part of a heat engine. And we're asked, so it raises temperature of benzene from 20 to 60 degrees. It's isobaric. The surrounding temperature is 65 degrees C, and we're given a heat capacity. So this looks like a heat engine kind of problem. So we have given the input and output, what is changes in enthalpy for the process. So this probably involves balance of energy, right at the bottom of the page, well, I guess now at the top of the page, the energy balance equation, looking at an ideal thermal unit, Q equals delta H, or at least first all law balances. I suspect this problem will start talking about entropy, so probably top of the page, we see entropy balances, and perhaps it gets into efficiency. I don't know why I'm pretending I have not read the rest of the problem. Okay, so part A is about looking at an enthalpy change. By the way, the students would also have an equation sheet that would probably tabulate how to calculate an equation for delta S and delta H. Okay, so now assuming the heat exchanger could perform both heat and work on benzene, perform an energy balance. Okay, that's what we expected. What does the first law tell us about the relationship between delta HQ and W? Part C, what is the maximum amount of heat that would be allowed to be transferred according to the second law? So that's probably an entropy balance. I know it's an entropy balance. What is the ideal work done? That is probably in the limit of reversibility. And then comparing it to a Carnot cycle where your Q is QH and then you have a TH and a TC. So that involves looking at Carnot efficiency and conversion of heat into work. So it looks like we're touching on a lot of topics, in the scope. Okay, so problem 3 is a Clausius-Clapeyron equation a good model for saturation pressure of water near 100 degrees C? Justify your answer using the steam table provided. So we have volume, enthalpy. The Clausius-Clapeyron equation is at the bottom. Well, it just says Clapeyron equation, but the Clausius-Clapeyron is a simplification, and the equation sheet goes into the different forms. So how would I approach this exam? So I would start by choosing something that I considered fairly straightforward to warm up. In my opinion, problem 3 is kind of the best place to start because I can write out the Clausius-Clapeyron equation and then show which numbers I would need from the chart in order to actually test what the problem wants us to test. In other words, is the Clausius-Clapeyron equation a good assumption? So I think that would be a place to start where I think it'd be fairly straightforward. Now, problem 2 is largely conceptual. So if you have, if you're comfortable with entropy, energy balances, things like that, I hope you are. It looks like there's nothing too confusing or crazy about this question, so I might do this next. I would write out the equations before I started cranking out numbers, just like with problem 3. Now, problem 1 is probably the most difficult, thermocalculus, and so I might save that for last, but of course, I do recommend giving it a shot. In the next videos, I'll solve problem by problem, and we'll sort of sketch out the answers conceptually first before plugging in numbers.